appreciate the opportunity to be here today. And normally it gets around this time of year, and I like to talk about, a lot of places I'm talking, they're talking about how cold it is. And one of the things I always liked about growing up in the Midwest is you get there, and then typically about every third or fourth year, you got a stretch of time where it never gets above zero for about a week or two. But I can't really tell that story because you guys all know that anyway, because that's what happens where you guys live. So it's not impressive anymore, but or at least with this group. But no, I just appreciate the opportunity to be here. And this is a question that I have thought a lot about, in part because I think this is one of the areas that touches where Christian apologetics and science touch on one another a lot, or actually intersect a lot. And as I joined Reasons to Believe, I had talked about finding evidence for a beginning. I've talked about all sorts of things. And I had an opportunity, I think it was back in 2014, to go over and speak at the Unbelievable conference over in London, and shared the platform with William Lane Craig. And that was kind of exciting to be able to talk with him a little bit. And I got to give a talk about the evidence for a beginning. And I talked about the evidence for beginning and evidence for design in the universe. And I'd given, laid out what I thought was the evidence. And there was a fellow out in the crowd who stood up and raised his hand and asked me a question about, I'd said something about quantum gravity, didn't quite, I was trying to understand the question. I gave an answer, but I don't think I really answered his question. I got done with the talk and was interacting with folks, and he kind of waited there for a while. And after I'd talked to everybody, he walked up to me and he goes, I see what you're saying, but I don't think you can say there's evidence for a beginning. And this is why. It's because, I've got this quantum gravity model, and I can show 3 or 4 or 5 of them that show that there is no beginning to the universe. And that challenge weighed heavily on me for this reason. We need a quantum theory of gravity to answer this question. And here was this fellow who said, I've got 4 or 5 different models that show that we don't need to have a beginning. And so I was thinking about that because, and then you'll kind of see where I ended up with that. But as I thought about that question, I realized, I need to take into account this new data and ask the question, is there still evidence for a beginning? And so what I want to show you today is kind of what I have, the conclusion I have come to about whether there's a beginning or not. And to start there, I guess I just want to start by asking the question, did the universe begin? And as we look at that, I want to lay out some evidence of why we think it did. And to do that, we kind of need to start back in the 1900s, whereas scientists were looking at the universe. The idea was that space and time were just this universal absolute quantity, that space and time were everywhere, that they had existed forever, matter and energy and things interacted within that space and time, but space and time were kind of the fundamental essence that everything happened in. And in that sense, space and time are infinite and eternal. So they've gone on forever, they will go on forever, and there's no beginning as a result of that. And some other things that scientists thought about the universe, they thought that the universe was static. Now, this was back before we discovered galaxies. We knew, we knew that planets orbited, the planets orbited around the sun. Sun probably moved in our galaxy. We knew those sorts of things. But when you looked on large enough scales, the universe was just static and unchanging. And given that we only knew about gravity and electromagnetism, we thought that, there was this interesting phenomena that as you moved through the universe, the laws of physics appeared to change, or you could tell where you were and how you were moving based on the way the laws of physics looked, because the way things changed in electromagnetism was different than the way they changed in Newtonian dynamics. And so that was kind of the picture of the universe at the start of the 1900s. But in the early 1900s, starting in 1905 and then culminating in 1916, Einstein published this revolutionary theory. And the genesis of that theory was actually that later subtle point that the laws of physics seem to vary as you move through the universe. Einstein actually, philosophically, he just didn't like that idea. And so he asked the question, what would it take to build a model of gravity where you could not tell where you were based on your location or your motion? And he set about building that. And he looked at what happens when you're moving at uniform velocity. What sort of theory would you get? That's where you get the theory of special relativity. It turns out that's the easier one to do. And then he's also working on acceleration and gravity. How would that work? And that's where he ended up coming up with the theory of, or the general theory of relativity. And the key point, or one of the key points about the theory of general relativity, is that it explicitly codifies the idea that the laws of physics don't depend on your location or your motion. So when I turn on a flashlight, or I see light moving at the speed of light, if I turn on my flashlight, I will see light propagating away at the speed of light. And if I move that flashlight at close to the speed of light and right on top of the flashlight and turn the flashlight on, I still see the light beams moving away at the speed of light. And so that's one of those fundamental characteristics, is that everybody measures the same velocity of light, and light always moves at the same velocity. But again, the key point is that the laws of physics now, our model of the laws of physics show that the laws of physics don't depend on location or motion. Well, as he looked at this, the generic solutions of general relativity predicted an either an expanding or a contracting universe, that space and time were now dynamic. And so this radically changed the way we thought about space and time. And this notion of, does it have a beginning? Has it gone on forever? Those questions now became part of the scientific investigation that we could do. Now, Einstein thought it was static, and so did everybody. And, I actually introduced the constant to get that outcome. I don't know philosophically all the motivations for that, but at least part of the motivation was because if it was static, that you could maintain this past eternal universe, and there was no beginning to things. Fast forward now about 15 years, astronomers had been looking out at these blobs, these island universes out in the universe, or out in space. We now call them galaxies. And people had noticed that the spectral lines from these were actually redshifted. And that's a sign that it's moving. And what Hubble was able to do was to be able to make a measure of how far away these galaxies were and put that all together. And what he recognized was that as a galaxy is more distant from us, it is moving away from us faster. And that's the telltale signature of an expanding universe. So we have Einstein comes along and says, hey, laws of physics are constant no matter how you're moving or where you are in the universe. That leads to this idea of a dynamic universe. Now you have the discovery that, lo and behold, our universe is expanding. That naturally leads to the question of, well, if it's expanding, what happens if we run time backwards? Do you end up getting to a place where everything is in the same place and you end up getting a beginning? And that's the idea that was out there, people were wrestling with. And, this is kind of the picture that people had, that, you've got this blob that blows up and everything's expanding out from it. And this is kind of the prevailing picture. And I really hate this picture, and I'm showing it to you in part to say this is the wrong way to look at things. Because this gives the picture, the idea that there's a sphere of stuff that's exploding, that the universe is this sphere and it's expanding out and there's a center to it, and it's just the wrong way to look at it. But this was the picture that a lot of people had, that we thought that there was a bound to the edge of the universe, so now we could see where it is, or you could in principle see out to the edge of it. But this was the prevailing picture. And so it really does raise this idea that perhaps there's a beginning. Now, fast forward to the 1960s, people were doing research into black holes. And one of those people was Stephen Hawking. And what they were able to find is that if you take a group of particles and you just allow them to collapse, gravitationally collapse on themselves, they will collapse down, 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 and eventually, so you see the trajectories here, eventually those trajectories will cross, and where they cross, you get infinities. That's where you get the infinities. The laws of physics break down, and you can there's no way to talk. So if our laws of physics, if these laws of physics are at a correct model of the universe, and we thought they were, because general relativity is very successful at predicting how things work, then as you go into a black hole, you eventually run into a boundary where space and time cease to exist. Hawking's work took that work and applied it to the universe and said, all right, if we now, because with a black hole, you can define everything well and do the calculations precisely, but he's saying, all right, can we apply that to the universe, where if we take the universe and run time backwards, do we run into the same sort of scenario? And he found that, lo and behold, if general relativity is an accurate description of the dynamics of the universe, and if we have a certain amount of energy in the universe, and we could demonstrate that both of those were correct to all the sensitivity we had, there were two other qualifications about not having closed time-like curves and that energy behaved a certain way. But if those four conditions hold, then lo and behold, as you run the universe backwards, you eventually run into a boundary where you get the singularities, and that is a good description of a beginning. And these singularity theorems are what said, yes, it really does look like the universe has a beginning. And so you go to the 19, I think the paper written on this was in 1969, 1970. And so really the idea was that we had a beginning. And so this now fast forwards to the question I got from this person in the Unbelievable conference. And I'm like, okay, so I can point to all this evidence, but he's saying, wait a second, quantum gravity looks like quantum gravity gets rid of the beginning. And so let's go kind of motivated why we think the universe might have a beginning. Let's now expand on or discuss the weight of this person's question and ask why it might not. Well, if we, I would do a little quiz here, but I'm going to assume everybody knows that this is a picture of the moon. And the moon is this fascinating, one of the fascinating things about the moon is that it's about 200,000 miles away from us, which means that it takes light about 1 second to get from the moon to us. Implication of that is that when I look at the moon, when you look at the moon, we are not seeing the moon as it is right now. We are seeing the moon as it looked 1 second ago. You think, okay, that's not really that big a deal. Let's move out a little further away. If we go to the sun, we get to about 8.5 minutes, but if we get out to the Andromeda galaxy, it takes light about 2.5 million years to get from the Andromeda galaxy to us. That means this picture is not what the Andromeda galaxy looks like now. It's what it looked like 2.5 million years ago. And if we continue to move further out, we can go out and look at the Hubble Ultra Deep Field, and there are galaxies in this object that are anywhere from 10, 11, maybe 12 billion light years. The light has been traveling toward us for 10 billion years, which again, the point of that is that it means that we're seeing the universe, these objects, as they looked 8, 9, 10, 11, 12 billion years ago. And if we continue to push even further out, we eventually run into the cosmic microwave background radiation, which is the most distant thing that we are capable of observing at this point in time. And we're seeing this as a picture of the universe as it looked almost 14 billion years ago. Now, why do I make that point? Well, if we go and say, well, what did it look like a little further away? Now we're getting to a place where light has not had enough time to traverse from that location to the Earth. So we can talk about an observable universe, the maximum extent of stuff that we can observe, which raises an interesting question. Is there more stuff out there? And the answer is almost certainly yes. And so the picture of our universe as we talk about it today, it's not this little blob or sphere that expands out and grows very rapidly and eventually becomes this thing that we call the universe. It's really more something like this, where if you were watching it, the universe would just be there. And we could go and make measurements between two objects and say, all right, as time goes on. What you'll notice here is that I marked out the objects. It's froze it and marked at a specific time, and then waited until it expanded more. And you'll notice that the smaller the distance was between two objects. Let's see if this works. Yeah, so we got, if we go between these two objects, it started with a smaller distance and it grew by a smaller amount. Whereas this one here was farther away and it grew by a much larger amount. Like I said, that's the signature we see of an expanding universe. And so we live in this expanding universe, and we're going to let it continue to go now here in just a second. You see it goes out, and if we were to now zoom out, we could see, all right, we can see out much larger. But now what we know is that we live in this region called the observable universe, but given our understanding of the universe, certainly there's a whole lot more stuff out there. And this raises the idea, or part of why we think this happened, is that in order to explain our universe, we need this epoch of inflation, where very early in the history of the universe, it expanded at a much faster rate. It was expanding, I mean, it's expanding exponentially now, but it's just at a much slower rate. Whereas early in the universe, it was expanding at a very rapid exponential rate. And that means that stuff exists beyond our ability to see. And so if inflation happened, we live in this kind of multiverse. Now, the interesting part about that is we can now talk about, so what is the multiverse? Well, I've talked about what the observable universe is. Now we can just go and ask the question, all right, so our observable universe is part of a much larger realm. But the reality of it is, when people talk about a multiverse, they're talking about other realms that are out there. And my thinking on the multiverse, not as it interacts with Christianity, but whether it exists or not, has kind of it's kind of gone different places. But as I've looked at where we stand now, if inflation happened, we live in that level 1 multiverse. There's just a whole lot more stuff than what we can see. That's a non-controversial idea in my assessment. If our mechanisms for understanding inflation are correct, then we live in a level 2 multiverse. Now, that is a bigger if, but I just kind of assume we're going to have all my discussions in the context of a multiverse exists. I think there may be reasons why it doesn't exist, but it seems like if inflation happened, a level 1 multiverse exists. If our mechanisms for understanding inflation, this type of level 2 multiverse actually exists also. And I find that a fascinating way to look at the universe. Why I bring this up is because the mechanism that drives inflation has implications for whether there's a beginning or not. I'll come back to that in just a second. Excuse me. So does the multiverse avoid a beginning? Well, so the picture of inflation, again, if you go back to that picture of there's a sphere and it expands, well, inflation just happens where that sphere expands very rapidly. And again, that's just a wrong way to look at it. The way to look at it is there's this stuff that inflates and it's not in its ground state. And so it will decay to the ground state in places. And where it decays to the ground state, you get this bubble where things expand more slowly. And our universe, or the way to explain our universe or inflation, is that our universe is inside one of those bubbles. And it would be very weird to just have one bubble. And so there's certainly more bubbles out there, which means that if we can talk about how our bubble may have had a beginning, but there may be other bubbles out there that have beginnings far, that could just, once inflation starts, it seems to go on forever. So the question is, maybe it's always gone on into the past. Turns out that that's not the case because, Arvin Bourdet, Alan Guth, Alexander Vilenkin, 3 people who are very prominent in developing inflationary cosmology, show that under very generic geometric conditions, where the singularity theorem of Hawking and Penrose had general relativity's got to be true, and there's got to be enough mass, and energy has to behave a certain way. Well, the way inflation works violates that energy condition. So if inflation happened, the Hawking-Penrose singularity theorem no longer applies to our universe, and it doesn't point to a beginning. Well, what Bourdais, Guth, and Vilenkin were able to show is that a more generic principle, there are still some conditions to this conclusion, but if their conditions hold, and again, they're just kind of simple geometric conditions, they show that inflationary spacetimes are incomplete in past directions. What that means is that if you go backwards in time, in an inflationary spacetime, you eventually run into a boundary, which again is a marker for a beginning. So even a multiverse has a beginning. So we still have this evidence for a beginning. Now, one other piece of physics that we need to understand to grasp this conversation, or grasp to understand this conversation, is that when we talk about our fundamental forces, we talk about the electromagnetic and weak nuclear, gravitational force, strong nuclear force. But as scientists have been working on those, what they realize is that these are not independent entities that exist, because if you go back earlier in the history of the universe, it was hotter. And it turns out that the electromagnetic force, even though we see them as separate today, were actually one and the same force. They're unified is the terminology we use. And we find the particles that come out of that. There have been about five Nobel Prizes that have been awarded in this work, 3 for theoretical work, 2 for experimental work. And the discovery of the Higgs boson actually was the 5th one that solidified that, yeah, this is the right way to look at things. Well, we were so successful at unifying the electromagnetic and weak nuclear force, scientists think that not only will the strong nuclear force be unified, but so will this gravitational force, and we'll end up with this quantum theory of gravity. Now, think back to what Newton did. When when he was looking at gravity a certain way, space and time were just these quantities that existed that things moved within. Well, now what you have is a scenario where space and time are dynamic. So the introduction of general relativity changed the way we thought about space and time. Well, all of these theorems, the space-time theorem, or the singularity theorems that Hawking and Penrose developed, the theorems that Bourdais, Guth, and Vilenkin developed, they're all classical in that they don't deal with quantum mechanics. And so the thinking is, perhaps when we get this quantum theory of gravity, it's going to radically change how we think about space and time. And even talking about a beginning will no longer be something that is relevant. And so that's the idea. That's the weight behind the question this fellow was asking me. He's saying, we're looking towards developing these quantum theories of gravity. The ones that we have out there today, most of them seem to say there's no beginning. So really, we can't say there's strong evidence for a beginning. And his assessment of the quantum theory of gravity, the need for it, I agree with. The idea that there are multiple theories out there that say there's no beginning, that's correct. So now I have to say, all right, given what I know, how do I make a reasoned case, or can I still make a reasoned case that there's a beginning to the universe? And so these are some of those quantum gravity models. You know, you have models where the universe contracts from past infinity, it goes into this bound, it kind of goes to this phase, and the quantum gravity keeps it from producing a singularity and it rebounds. You've got cyclic models, you've got hibernating models, you've got reproducing models. Again, the point is not to understand all the models. The point is to recognize there are numerous ways of looking at quantum gravity models where you end up without a beginning, even though we can still talk about a time from a certain place. So, here's why I am still confident that we live in a universe with a beginning. So if we go back to our universe, as scientists were introducing this, when Einstein first introduced this, one of the thoughts that came up, and again, I'll use this bad picture here because that was the picture at the time, is that, okay, yes, our universe may be expanding or contracting, but it's actually expanding and contracting and expanding and contracting, and it's oscillating back and forth. And scientists propose this. I'm going to stop that just so that you don't get sick looking at it. Scientists thought, well, you know, this could just go on forever. Well, they looked at it from a thermodynamic perspective, and every time things expand, you lose usable energy. So each time the expansion is going to get larger and larger. And so it may expand, but each expansion grows. So if you extrapolate that back, you still end up with a beginning to things. And so this oscillating universe was one way to get around a beginning, but it didn't work. Another idea that was popular and thought for a much longer period of time, probably 2, maybe 3 decades, was the idea that yes, the universe is expanding, but as it expands, new matter is created. And as you look at the universe, it just looks the same over time. Now, I think one of the things I want to point out in that is that's a pretty radical concept, but yet when people introduced it, it was like, yeah, that's scientific. We can test that because you're saying the second law of thermodynamics, that energy is neither created nor destroyed, is no longer valid. That's not the second law. That's the 0th law. The second law is that entropy always increases. But the idea that matter and energy can be created and that's what the universe does, that's really kind of a radical way to look at things. But you end up with this steady state universe. And so this was thought to be the answer. We know the universe is expanding. This gives you a past eternal universe, and it means that, okay, we no longer have to worry about a beginning. Well, it turns out this model predicts that we should make certain measurements when we look out in the universe. And lo and behold, when we look out into the universe, it doesn't match those predictions. So this one cannot be correct. In fact, the biggest experimental piece of evidence that shows this model is incorrect was the discovery of the cosmic microwave background radiation, because it shows that the universe was much hotter in the past instead of being the same at all times. There were also some works on quasars. The measurements of quasars show that this is not a right way to look at it. And so as I began realizing and researching and investigating this, what I realized is this, is that if you go through the 1900s, you start in the early 1900s, the universe was static and eternal. So there was no beginning because that was just not even the right way to think about things. Well, Einstein develops this theory of general relativity. Now we have this idea that there's a beginning to the universe, or at least it's within the realm of possibility. He introduces this cosmological constant to get a steady state universe, or a static, not a steady state. Steady state and static are two different things. To get a static universe, which has no beginning. In that time, people also developed this oscillating universe model. And so we've got these two models where general relativity is the correct way to look at it, but you end up without a beginning. You get the expanding universe. Okay, so we know that the universe is expanding. That says that this static model is not correct. So more measurements of the universe show that static model is not a correct way to look at it. With the oscillating universe, you have these thermodynamic problems, and so that still doesn't get rid of a beginning. But now you've got the steady state universe being around for quite some time, and it's not until the cosmic microwave background is discovered, and then ultimately that led to the work that came up with Hawking and Penrose developing these singularity theorems that show no, even this steady state model doesn't get around the beginning. Well, now you've got inflation that comes in, and again, this was ultimately driven to explain some problems in trying to unify the laws of physics, but you get this inflationary epoch early in the universe, and that seems to get rid of a beginning. And you end up with this multiverse that even if our universe might have had a beginning, the multiverse seems to go on forever. And lo and behold, there are these, again, singularity theorems that show that even in a multiverse, even with inflation, you still end up with a beginning. So now we're dealing with quantum gravity models. And the question is, are these going to get rid of the beginning? And as I recognize this, as I understood all of what has happened over the last 100 years, what I've recognized is this, that seems to be this drive towards finding models of the universe which are past eternal. Some of that's probably philosophical. Some of that is, driven by the actual physics, because there's a symmetry to not having a beginning to the universe, and physicists really like symmetry. But there's this drive to find models of the universe that don't have a beginning. And so there's been numerous ways people have proposed to get around a beginning. Maybe the universe oscillates. Maybe there's a steady state. Maybe inflation. Maybe the multiverse. Maybe quantum gravity. And when we go look at where we have data that evaluates where we can answer the question, every time scientists have proposed a model that gets around a beginning, the universe keeps pushing us back to the models where there's a beginning. And so what this fellow is really asking of me is to say, hey, maybe this latest way of getting around a beginning is the one that's really going to work. Now, I think it's reasonable to ask the question. But as I look at it, what I say is, I'm confident that there's a beginning because scientists have spent so much effort trying to get around the beginning, and the universe seems to keep pushing us back towards models where there's a beginning. And that's exactly what I would expect to find if God indeed created the universe and there's a beginning to it, as he's revealed in Scripture. I would expect to find that as we test, as we probe, as we push, we're going to find that the best explanation is one where the universe has a beginning. So did the universe begin? Well, the 20th and 21st centuries are littered with models that avoided a beginning, only to have the universe inevitably push us back to the idea that it began to exist. So I am very confident that the universe began to exist. I'm going to leave that slide up there. I'm going to throw it up for some questions here before I wrap up after a while.